Imagine all of human scientific knowledge is about to be wiped out. If you could pass just one single sentence to the next generation of survivors to help their rebuild, what would it be? The great physicist Richard Feynman had an answer. Without our accumulated knowledge of physics, chemistry, and biology, humanity would be starting from absolute scratch. We'd lose our understanding of medicine, engineering, and the very mechanics of how the universe operates. Feynman's sentence to save science was what he called the atomic hypothesis. He stated it like this: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. This one sentence serves as a starting point. If you accept that matter is made of moving, interacting particles, you can begin to explain why a gas expands or why a liquid flows without needing any other complex assumptions. The concept of an invisible, indivisible building block of matter didn't start in a modern laboratory. People chased this idea for thousands of years based purely on intuition. In the 6th century BC, the Indian philosopher Kanada proposed that matter was made of eternal, indivisible particles he called paramanu. A couple of centuries later, the Greek thinker Democritus theorized that everything was constructed of tiny individual shapes, but those early concepts were just philosophical guesses. It took until the early 19th century for the English chemist John Dalton to ground the atom in quantitative data, using measured chemical reactions to prove that elements combine in fixed, predictable ratios. The transition from intuition to measurement allowed scientists to link the mass of a visible substance directly to the number and ratio of the invisible atoms inside it. To see how Dalton's mathematical rules dictate the objects you interact with every day, we have to scale down to the atomic level. We measure this realm in angstroms. 1 angstrom is 1/10,000,000th of meter. Using tools like electron microscopes, we can now physically observe matter at this exact scale. Look closely at a solid piece of matter. The atoms are packed tightly together, usually just about 2 angstroms apart. They vibrate, but short-range attractive and repulsive forces lock them firmly into a rigid structure. If you add enough heat to melt that solid into a liquid, the particles remain roughly 2 angstroms apart. However, those rigid forces unlock, allowing the atoms to freely roll and tumble over one another. The atoms themselves never change. A hard stone and a flowing river behave differently, purely because of the invisible spatial rules governing how their particles interact. If solids and liquids are defined by how tightly packed they are, gases are defined by their sheer emptiness. When a liquid becomes a gas, the distance between particles expands drastically to tens of angstroms. They completely escape those short-range interactions and fire off in straight lines. This brings us to a crucial measurement in kinetic theory, the mean free path. This diagram illustrates the mean free path, the average distance a single gas molecule travels before colliding with another atom. In a gas, that uninterrupted flight can span thousands of angstroms. Because they spend so much time flying freely through completely empty space, uncontained gas molecules will continually spread outward until they fill whatever environment they are inside. If you look closely at a sealed glass jar full of air, or even just the quiet room you're sitting in right now, nothing appears to be happening. The air is entirely still. But that stillness is an illusion. Inside that quiet jar, billions of molecules are slamming into each other and the glass walls at hundreds of meters per second. This split-screen visualization illustrates a concept called dynamic equilibrium. Individual molecules are endlessly colliding, exchanging energy and altering their independent speeds. But collectively, the rate of these microscopic impacts remains steady, meaning the macroscopic properties, like the pressure reading on this gauge, stay completely constant. In the 19th century, scientists like James Clerk Maxwell and Ludwig Boltzmann developed the kinetic theory of gases to prove exactly how this microscopic chaos yields macroscopic stability. The atomic hypothesis remains our best tool for understanding the universe because it explains that the stillness we see around us is actually the result of billions of individual high-speed collisions happening every second.